Hi, we're going to start our first topic in Chem 266. So in this block, we're going to go over all the basic ideas in physical chemistry. And I chose to start with quantum mechanics for two reasons. It's probably new to most of you unless you've taken a modern physics class. And so it should be interesting, I hope. And it's also the basis of all spectroscopy. So it's something that you haven't really seen, but you've applied it. So it's a good thing to really focus on this when we're fresh at the start of the block. And the other reason is our computational physical chemistry book that we're using starts with this topic and it builds. And so unless we start with this topic, we'll kind of have to jump into that book at a time when you don't know all the Mathematica. So I am going to share my notes. Okay. And I hate this. Okay, that should work. So I will also post these notes. I don't know if they'll be helpful or not. Most things I'll do these recorded lectures and I'm redoing them. I had done them during the pandemic the first time I taught this class, and I just sort of thought that it was a good time. The course has changed enough um, over the last few years that I feel like it was time to redo them. So most of the material we cover, I'll do these pre-recorded lectures, which you can watch as an option, or you can read the chapter yourself. And then when we come to class, we'll focus more on working problems and answering questions. So quantum theory, what is quantum theory? So we're going to learn about the basic principles, and then we're going to learn about the applications to the three important kinds of motion within a molecule. So that's translation. A molecule can fly through space. You can throw it like a baseball. It can rotate and it can vibrate. So these are all things that you've heard about in other classes, such as organic. And so now you're really going to see where the quantum mechanics will take you mathematically. So the first one, 7A, is why we discovered that we need quantum mechanics. So the emergence of this new theory. So what's the experimental evidence? There are several things, and you did learn about this in Chem 107. Number one is that we see discrete energy levels. And so that means that, as you recall, each and every atom, if you start with atoms, when it interacts with light, gives off characteristic wavelengths. Doesn't give off a continuous type of light, it gives off just characteristic ones. And as we go through this, we'll remember that light of a different wavelength has a different energy. So we also need to understand the photoelectric effect and then that electrons have wave properties. So these are all three different kinds of experiments. So this is about 1900. And so when you think about the times we were creating new instrumentation, so we were able to measure the properties of electrons, which hadn't been true before. So before this time when you could actually see like the discrete energies or the wave properties of electrons, we didn't have an understanding that electrons weren't acting like big particles, like baseballs and other things that we knew just followed classical mechanics. So I want you to stop and read the Chemist Toolkit, number 18. And I crossed off the page number if you have the international version of the book versus the American version of the book. The pages are different. Probably there's more stuff in the preface or something. And so I'm just left off the page number, but the toolkits have the same number. So this is just to remind you of the properties of radiation. Um, and let me, I think, I think because you're reading that, I'm not going to pull up the figure for that. But you remember that electromagnetic radiation has wave properties and that it has an electric and a magnetic field. And so the only thing that's rather new, so we talk about wavelength and frequency, but then we also introduce a new definition of how to characterize a type of radiation, and that's the wave number. And it's simply 1 over the wavelength. And that's often used because it's proportional to frequency, and frequency is proportional to the energy of a photon, we'll see. So we are going to look at these diagrams. So the first experiment, so these experiments are looking at how electromagnetic radiation interacts with the electrons and atoms. Therefore, if you don't understand what electromagnetic radiation is, or don't remember that, that won't make a lot of sense. So I am going to see if I can share the share. Why is it there? Oh, there we go. Kind of a pain. Every time you want to use a different screen, you have to shut it off, the share, and then pull it back up. So, okay. So, electromagnetic radiation, I said, has two different fields. It has a magnetic and an electric, so they're perpendicular to each other. We tend just to think about the electric part when we're talking about how electrons interact with the radiation, because negative particles interact with the charge field. You've already looked at things like NMR, where we also have to worry about the magnetic field, but we will pretend that we just have a planar wave and that it's the electric component of the electromagnetic radiation field that we're looking at. So this just reminds you that light is moving, and so it's propagating, in this case, to the right. And the definition of the wavelength is the distance between two peaks. This is just the electromagnetic spectrum, so it's showing you the different frequencies, and therefore, yeah, the different frequencies wavelength on the top because they're related to each other, just to remind you of the different regions. So light has different amounts of energy, all the way from radio waves to cosmic rays above gamma rays. So the energy increases as you go from left to right on this. And this is the first experiment that we're talking about, this idea that electrons can only absorb characteristic wavelengths. So this is an emission spectrum. So it could either absorb or emit. So if you excite the electrons in an atom, the light will come back off as the electrons fall back down in energy, and you'll only get certain wavelengths. You won't get a continuum. And so this was a totally new idea. So if you're looking at molecules, it's very, very similar, except that molecules have so many different places to put energy compared to atoms. So you don't get those nice peaks, but you get spread out peaks that have fine structure. So might be the electron moving, also the molecule changing rotational state, something like that. And so the important thing that comes out of this is the idea of the Bohr correspondence principle. Well, no, the Bohr principle, it's not the correspondence, that's a different one. So this is just the idea that we know that if the electron is going down in energy and giving off light, that that photon of light has to have an energy that's equal to the difference of the two energy states. Okay, so now I'm going to go back to sharing my notes as quick as I can. Okay, so the Bohr frequency condition, that the difference in energies of the electron is equal to h nu, and h nu is the energy of a photon of light. So take a little break and do self-test 7A.1. I also got rid of the page number because it's not the same in every book, but just stop and do that so you're confident you remember this idea of the Bohr frequency condition. Okay. And so this idea of discrete energies is the same idea as saying the energies are quantized. They don't come in a continuous value, they come in only certain values. And so how do you explain that? So these experiments, like I said, were being done in about 1900, but we really couldn't explain it because big particles, if you throw a baseball, you can throw a baseball with any energy that your arm can give that baseball. It's not, you can throw it 1 mile an hour, 10 miles an hour. It doesn't have discrete values. And so the electrons were behaving very, very differently with these new experiments than big particles were. And so moving from that, we'll be able to explain these discrete energies in just a little while, but we have to put it into the context of other experiments that were taking place at the same time. So I think it was 1905, Einstein got the Nobel Prize for his interpretation of the photoelectric effect experiments. So we'll look at what that means in a second. But he was able to interpret those experiments to mean that light, electromagnetic radiation, which we knew to have wave properties, also had particle properties. So let's take a quick look back at the um, at the figures from your text. Okay, so this is a picture of what happens with the photoelectric effect. And so what's happening is you're shining radiation onto a metal surface. It has energy in the ultraviolet region. That's how much energy this takes. And when you do that, energy or electrons will be ejected from the surface if the radiation has the right frequency. So, and when it comes off, the arrows are showing you it comes off at different angles, and the electrons come off with different energies. And so, yeah, so this is showing you what Einstein interpreted that to mean. So if you have the line on the left, that's the energy of a photon that's being absorbed. Some of the energy, as you know, has to go to actually pulling that electron off. The electron is in an energy orbital in the metal, so it's attached to the metal. So this right hand arrow is showing you that there's some amount of energy. It's called the work function that's taken just to remove the electron from the surface. And then if there's any extra energy, it will go to the kinetic energy of that electron moving away from the surface. And so this is just essentially the same graph, just showing you that if you have a photon of energy that has exactly the work function, there's going to be zero kinetic energy. But if the photon has more energy, it's going to then give that kinetic energy to the electron after it's used to pull it from the surface. And that's and so the important part of this experiment is that there's some threshold frequency. You can make the light more intense, so make it brighter, but if it has the same wavelength and frequency, until it gets to some threshold, you'll have zero electrons being pulled from the surface. And then that the kinetic energy varies in a linear way with frequency, and that the intensity plays no role. It only means that there are more electrons coming off, but it doesn't improve it won't make an electron come off if you don't have that threshold frequency. And so the equation that Einstein came up with is that the kinetic energy, so on the left-hand side, is equal to h nu, which is the energy of a photon, minus the work function, which is the energy it takes to pull the electron off the surface. And when you look at this is a straight line. It says it varies in a linear way. And that's because the kinetic energy, if you looked at this as y equals mx plus b, the slope of the line would be Planck's constant. The intercept would be minus the work function if you were plotting the kinetic energy versus the frequency. And so Einstein came up with the idea that of this light having particle nature, and the particle that the particle name is a photon. So the energy of a photon of light is equal to h nu. It's equal to Planck's constant times the frequency of that light. So stop and do self-test 7A.2, which is just using that equation. And so from this, it was concluded that light, which was thought to be wave nature, also has particle nature. And so that's huge. And so the first postulate that was came up with in order to explain this discrete energy idea for electrons was that what if particles can also be waves? So photons are particles of light. They're not really particles in the same sense, though, because if you stopped a photon from moving, it would have zero mass. So there's a distinction between the characteristics of light and particles as we know them in that way. So if we talk about other particles, particles like electrons, where if you did stop them from moving, they would have mass. That's the distinction when we talk about a particle versus a photon. So what if particles could also behave as waves? And so you can look at experiments where you can actually show that. So let's take a quick look at a graph of an experiment that shows that idea. Huh, I thought, huh, this doesn't have the complete set of figures from your book. Sorry. I thought that the PowerPoint had all of them, so I'll just have to explain it. So you know that waves can interfere in either a destructive or constructive fashion. So if you line up two waves at the same, so their peaks are the same, that'll be constructive interference and you'll get bigger peaks, but you can also line it up so the peaks and valleys are in the same place, and then that's destructive interference. So there were experiments done at this time that showed that particles behave like that. And so that electrons actually had interference patterns. They had this constructive and destructive pattern. And so that implied that these particles were acting like waves in certain situations. And so de Broglie was the first one to put that into some sort of math. And he said, okay, so if they have wave properties, we have to be able to calculate them. And so he said that the wavelength of a particle, lambda, is equal to h over p. So it's equal to Planck's constant h over p, which is the momentum of that particle. So stop and do self-test 7A.3, and then we'll continue to talk. So we will continue to talk about the wave-particle duality. So, and now what was concluded is that both radiation and particles have this dual nature. Electromagnetic radiation, which was thought to be waves, also has a particle nature that we call a photon. And then particles that we thought were particles such as electrons also can behave in a wave way. And so if we move from there into the next, these are called focus. So topic, or yeah, 7 is the focus, B is the topic. So going on to 7B. So now we want to think about the dynamics of microscopic systems. So with this new idea that particles can have wave and particle nature, this can be used to create an entire theory that will help us explain, for example, the discrete nature of the interaction, so the discrete spectra of atoms with their electrons and electromagnetic radiation. So in this, we want to be able to talk about all dynamic properties that can be known, and we'll find that they're going to be contained in something called a wave function. So out of this idea, if you go back up here, de Broglie said the wavelength of a single particle is Planck's constant over momentum, and that can be used, and it works well. But we need to think about, so what does that mean about a system, maybe a helium atom, which has a nucleus and two electrons? You can't really talk about the wavelength of each of those particles individually. And so Schrodinger's equation is this one in parentheses, which we're going to use and really understand. It says H times H operating on psi equals E psi. And so this little hat on the H is going to make it into a mathematical set of operations. So quantum mechanics is developed in two different ways. There's a wave way and there's a linear algebra way. And chemists tend to use this Schrodinger equation, H psi equals E psi. And so quantum mechanics is the theory that allows us to understand how small particles are behaving. So quantum mechanics says that a wave function psi in parentheses, right here, is a mathematical function that contains all the dynamical information about the state of a system. And we'll see that that's very useful, but contrary to classical mechanics, it gives us all the dynamical information about the state of the system that we can know, but we can't know everything. So we'll see and learn about things like Heisenberg's uncertainty principle, which shows us that it's different than classical mechanics. And so Schrodinger's equation, which I have up here in parentheses, if we write it out more explicitly, what it actually means, it means, so these things over on the left-hand side are operators. So H hat is a set of operations. So this says that this first term is some constants. H bar is Planck's constant divided by 2 pi. So negative H bar squared over 2 times the mass of the particle. Times you take the second derivative of psi with respect to x. And then you add to that it's called the potential function or the potential operator, but it's whatever the potential energy is. So it's something that's a function of position. We know that potential energy is the energy as a result of position of particles in a field. And so you multiply that by psi. And what you have to look for to get solutions for this is you get psi back, you get the same function back, but it's multiplied by a constant. So now this first term is called the kinetic energy term. The second term, this one is the potential energy term. Don't worry if this looks confusing. We will work through this in great detail as we go through the rest of this focus so that you'll really understand what this equation means. In the meantime, stop and read the toolkit 19 and 20, which just reminds you a little bit about calculus and differential equations, and will help you understand as we actually start to solve this equation. So the Schrodinger's equation says that there's a set of operations H that you operate on a function, and in order for it to be a solution, you have to get back a constant times that function. So this H is called the Hamiltonian operator, and that comes from the history of Hamilton's classical mechanics, where it's essentially a sum of the terms that would calculate kinetic and potential energy. So we're going to solve this for all the atomic and molecular systems that can be solved. So that will be our primary focus this week. So go ahead and skip the justification 7B.1. It's not going to be important for you. And now we'll go on. So this first description of quantum mechanics is very abstract because we're not actually making solutions. We're just talking about what it means. And after this, we'll go into great detail together in class, solving first the translational motion Schrodinger equation. And I think that will help put it into context. But we just need a little bit of understanding about what we're actually solving for. So you get this thing called a psi. What is a psi? So Max Born, who was one of the scientists working on developing quantum mechanics, there was Heisenberg and Schrodinger and Einstein and Bohr and Planck, so many people working on it. And so Bohr suggested once Schrodinger came up with this equation. So if you get psi, what does it mean? What does it mean for a system to have a wave function? And Born suggested that analogous to electromagnetic radiation, the square of the amplitude is interpreted as its intensity. So that's from electromagnetic radiation, and therefore the number of photons. So should be the same situation when you think about a system's wave function. Psi squared, so electromagnetic radiation squared, tells you the intensity. And psi squared from quantum mechanics is going to give us a probability distribution. So if you multiplied psi squared times some little volume, you'd get the probability of finding the particle in a small region of space of the volume delta V. And it's proportional to psi squared delta V, where psi is the value of the wave function in that region. So stop and do self-test 7B.1. Each of these, as you work through them, if you have problems, we'll start class and we'll look at any questions that you had with these self-tests. But that'll be a good way for you to see if you're understanding what I'm talking about. So if psi squared is going to give us a probability distribution, then mathematically, there are certain properties that psi has to have. So if it's going to be a probability, so from Born's interpretation that it's a probability density distribution, then the wave function can only have a single value at each position in space. If it had more than one, then that wouldn't make any sense. That would say you have a probability of finding the particle at that same location of more than one value. So you have more than one probability, and that wouldn't make any sense. So the functions that we use are going to have to be single valued. They can't become infinite over a finite region of space, because then if they did, they would say that we have an infinite probability of finding a particle there. And then from Schrodinger's equation, the wave function must also be continuous, so that the second derivative is continuous, and it must have a continuous slope everywhere. So if we take a quick peek at the pictures in your book that show those restrictions on the functions. There we go. So this is just showing you. So the first one has to be single valued. If it's not, if it looked something like this, then when you were at this location in X, you'd have 3 different probabilities of finding the particle. That makes no sense. If it goes to infinity over a finite region of space, that means when you look at that region of space, you have an infinite probability of finding an electron. That can't make sense. If it's not continuous, then there's a point where you have an undefined probability. And then if it doesn't have a continuous derivative, the same thing, then you can't take the second derivative in Schrodinger's equation. So when we look at solving Schrodinger's equation, we'll look at all the mathematical functions that are possible, but then we're going to have to take into account we can only use the ones that make physical sense. So single valued, can't become infinite, continuous, and a continuous slope or first derivative. So when we look at solving Schrodinger's equation next, we'll see that you get an infinite number of solutions mathematically, but only some are allowed because of the boundary conditions, and this leads to quantization. So that's going to be absolutely critical. So I guess this is the end of this topic. So the uncertainty principle is a similar idea to that the particle has a wave nature, but the uncertainty principle that Heisenberg starts with for his development of quantum mechanics, and he did it using linear algebra matrices. So we're not going to look at it, but it's an identical theory, just using a different type of math. But he came up to start with the idea, rather than thinking about wave and particle nature, he came up with there's a limitation on how well we can know the position and momentum of a particle. So he says delta x times delta p. So the uncertainty in position times the uncertainty in momentum is always going to be greater than or equal to 1/2 h bar. And remember, h bar is h over 2 pi. So the physical limit is this being equal, but if you're actually doing an experiment, you're always going to be greater than that because you'll have limitations on the equipment you're using to measure. So let's look at these figures. So okay, so different sine functions. This is hard to understand at this point, but we'll see when we solve the Schrodinger equation for translational motion that the solutions are sine functions. And if the solutions are sine functions, that means that the sine function has a definite momentum. And if it has a definite momentum, then we can't know anything about the position. So let's look at these two figures. Yeah, that's what this is trying to show you, that if you know exactly where a particle is, then the only way you can get a wave function that says the particle has all of its probability right there is to add up a whole bunch of different sine functions. So as you add more and more sine functions that have different wavelengths, you get a sharper peak, and it gets sharper and sharper until it looks like this. But so when you know this, you know exactly where the position is. You don't know anything about momentum because you had to add together a bunch of sine functions that have different angles, essentially. That will become more clear when we actually get our wave functions and start looking at their properties. So now just take a break, and that's the end of this section, and do self-test 7B.2. And I'm going to quit there and come back with another lecture in a little bit.